How do you put a telescope in orbit that's bigger than the rocket that's going to launch it? Is that even possible? Throughout history, our exploration of space has predominantly focused on uncovering hidden wonders that have long existed in the vastness of space. This is because space has a delicate balance, and while things are always moving, for the most part, everything has a pattern, and they stick to it too. But now, there's been an unprecedented event that challenges everything we thought we knew. Instead of merely discovering what was already there, we now find ourselves confronted with an inexplicable emergence, as if the universe itself has chosen to reveal a secret no one was expecting. The James Webb Telescope just detected 500 huge objects appearing in our solar system, and now we want to put a bigger telescope into orbit. How do you do that? This is where clever engineers come in. Join us as we dissect what these objects are and how they might change the way our solar system works forever. Discovering strange objects appearing isn't actually a new thing. Throughout the history of astronomical observations, there have been instances where it seemed that new objects had suddenly appeared within our solar system, but things haven't always panned out for these objects as we had hoped. One of the most famous cases came through the Kepler mission. This was an ambitious undertaking, aimed at unraveling the mysteries of exoplanets beyond our solar system. Armed with its remarkable ability to detect the tiniest fluctuations in starlight, Kepler's research unveiled a trove of exoplanet candidates. At first glance, these newly identified exoplanets appeared to be potential groundbreaking discoveries. However, as subsequent analysis and scrutiny continued, it turned out that more than half of the initially identified giant exoplanets were false positives. They weren't discoveries but rather misleading signals that presented themselves as genuine celestial objects. This was one of the biggest examples of how some discoveries can't be considered the cold, hard truth until lots of data confirm them. NASA's Transiting Exoplanet Survey Satellite, TESS, mission, designed to survey vast regions of the sky for exoplanet candidates, also faced instances where promising observations turned out to be fainter than anticipated. The light and shadows within the solar system challenged astronomers' ability to differentiate genuine celestial objects from mirages. A lot of work went into learning how to separate truth from illusion, and even more went into creating the perfect instrument that could detect objects as accurately as possible so researchers could skip straight to analyzing the data found, rather than running thousands of tests to weed out false positives. That instrument is the James Webb Space Telescope, JWST. The James Webb Space Telescope stands apart from its predecessors with its remarkable ability to peer deep into the early universe. Its large size and advanced instruments enable it to observe celestial objects and events that existed billions of years ago. It does this by capturing light from the most distant corners of the cosmos, offering a unique window into the universe's early years, and providing valuable insights into the formation and evolution of galaxies, stars, and planetary systems. In contrast to its predecessor, the Hubble Space Telescope, the JWST has an expanded capability to observe a much larger portion of the infrared spectrum. It does so in less time than Hubble. This extended range allows the telescope to get through dust clouds that usually block most visible light in the area. By capturing 6 times more light than the HST, it unveils intricate details and numerous stars within complex regions like the mesmerizing Carina Nebula. What amplifies all of this is its unique location in space, Lagrange point 2, L2. This point is approximately 1 million miles from Earth and is one of 5 stable points in space where the gravitational forces of the Earth and the Sun balance out. This location eliminates the interference caused by Earth's atmosphere, which can distort and absorb certain wavelengths of light. By being positioned well above Earth's atmosphere, the telescope avoids atmospheric turbulence, light pollution, and absorption, all of which can compromise the clarity and accuracy of observations conducted from the ground. This advantage allows the JWST to capture pristine, high-quality images free from the atmospheric distortions that plagued older telescopes, providing astronomers with a clear and unobstructed view of the universe and enabling them to study celestial objects with unprecedented precision. Additionally, the JWST's location in space allows it to access a broader range of wavelengths, particularly in the infrared spectrum. This is crucial because Earth's atmosphere partially blocks or absorbs various infrared wavelengths, limiting the capabilities of ground-based telescopes. Positioned far beyond Earth's atmosphere, the JWST can observe a wide range of infrared wavelengths without atmospheric interference. Leveraging the advantages of infrared observation gives the JWST the potential to make groundbreaking discoveries that were previously inaccessible. Older telescopes faced one more challenge: the cold. The JWST's space-based location allows it to operate seamlessly at extremely cold temperatures, which is essential to maximize its infrared sensitivity. The telescope's delicate instruments and mirrors need to be kept at frigid temperatures. What was a weakness for others is a strength for the James Webb Telescope. By being in space, the JWST can use a sunshield to protect itself from the sun's intense heat and keep its sensitive instruments at ultra-low temperatures. This cool environment enhances the telescope's ability to detect and study celestial objects that emit weak infrared radiation, such as distant galaxies, protoplanetary disks, and ancient remnants from the early universe. The James Webb Telescope is already making groundbreaking discoveries, having detected something thought to be impossible. It has found 500 huge objects that seem to have appeared out of nowhere. These objects are located in the Kuiper Belt. The Kuiper Belt, which lies just beyond Neptune's orbit, is a massive region within our solar system. It's home to a diverse array of celestial bodies, including comets, asteroids, and remnants from the formation of the solar system. These celestial bodies, collectively known as Kuiper Belt objects, KBOs, have distinctive characteristics that provide valuable insights into this fascinating region. The Kuiper Belt is estimated to be 20 to 200 times more massive than the asteroid belt, which is located between the orbits of Mars and Jupiter. The asteroid belt is a vast expanse of space hosting a majority of the solar system's asteroids, varying in size, shape, and composition, from small fragments to larger objects spanning hundreds of kilometers in diameter. These objects constantly orbit the Sun, influenced by gravitational forces, and occasionally collide. While the asteroid belt covers a significant distance, its overall mass is relatively small compared to other celestial bodies. In fact, the combined mass of the asteroids in the belt is estimated to be about 3% of the Moon's mass. Meanwhile, the combined mass of Kuiper Belt objects is less than 1% of Earth's mass, indicating that while the Kuiper Belt contains a substantial amount of material, it is relatively less massive than our planet. Kuiper Belt objects are predominantly composed of frozen volatile substances like methane, ammonia, and water. These icy materials, preserved in the cold depths of the Kuiper Belt, have remained relatively unchanged since the solar system's early days. The Kuiper Belt is also home to numerous dwarf planets, such as Pluto, Eris, Haumea, and Quaoar. These dwarf planets represent important remnants from the early solar system and provide insights into how the solar system formed and evolved. Estimates suggest there may be as many as 35,000 Kuiper Belt objects larger than 62 miles in diameter, with possibly 100 million smaller objects measuring less than 12 miles across. Scientists classify Kuiper Belt objects into two categories: classical and resonant objects. Classical KBOs follow stable orbits, largely unaffected by Neptune's gravitational pull, while resonant KBOs interact more significantly with Neptune, with their orbits in specific resonance ratios with Neptune's orbit. These interactions shape the complex dynamics of the Kuiper Belt. The three-dimensional structure of the Kuiper Belt provides insights into its composition, distribution, and overall nature. While the primary concentration of objects extends up to 10 degrees outside the ecliptic plane, there is a more diffused distribution that stretches farther. This three-dimensional expanse of celestial bodies indicates that the Kuiper Belt is not just a thin disk, but a massive region containing diverse objects with unique orbital characteristics. Determining the composition of Kuiper Belt objects is a challenge due to their distance and icy nature. These objects are primarily composed of water, ammonia, and methane, frozen in the outer reaches of the solar system. But their composition can vary depending on their distance from the Sun. Thanks to advanced technology like the James Webb Space Telescope, researchers are piecing together the puzzle of the Kuiper Belt, a task that would have seemed like science fiction just a few years ago. What are your thoughts on the Kuiper belt objects? Do you think they can surpass the significance of objects in the asteroid belt? Let us know in the comments below. If you liked this video, please give it a thumbs up, and as always, we'll see you in the next one.